All right, so I held that review on Friday, and I had what 9 or 10 students show up. I think it was productive. We covered a lot of the questions on limits and L'Hopital's rule and logarithmic differentiation. What I'm going to do is I'm going to lecture for the first, hopefully, 45 minutes to an hour, and then I'm going to address any other questions on the review, and for whatever we can get through that in that time period. Yes. Not. I don't think the entire review. It's too much work. Well, let's talk about what problems you would want to see me do off the review first, and we'll do that at the end, and then see how much is left. Okay. Yeah, no problem. All right. So optimization. All right. Optimization. We are still talking about this. The idea behind the optimization problems was to find what we called the objective function, find the constraint, and then use calculus to find optimum solution. And that's basically what we're doing. Usually when we find an objective function, we'll have a function, it'll be more like an equation. It'll have several variables in it, usually 2 in a Calculus 1 class. And then what we do is we find a constraint, which allows us to reduce the objective function to a function of 1 variable. And then we use calculus and what we learned about graphs of functions to figure out the highest and lowest values of that function. That's the idea behind optimization. So every problem is different. You know, no two optimization problems are the same. So the farmer with the fence problem is a classic optimization problem. Here is another classic optimization problem. So here's an example. Let's say that we have a sheet of cardboard in which we want to, well, let's say we know the dimensions. Let's say it's 24 inches this way, and let's say it's 15 inches this way. So we got this cardboard sheet, and what we're going to do is we are going to cut the corners out of this sheet. We're going to cut corners out like this. And those corners are going to be squares. So we cut those corners out, and we fold the sides up, and then we take this flat cardboard box and we make a container out of it. All right, so it'll be like this. When we fold up the sides, it'll look something like this. Do you agree? Now, it will not have a top to it, so it would actually be more like that, right? So we could come in here and we could fill this with whatever material product that we want to put in there. So we've gone from a flat sheet of paper to a three-dimensional figure. So this figure here has some particular volume to it, right? It can hold, you know, some amount of material. Yes? The question is, how should I cut it to get the maximum volume out of the container I'm creating? And then I'm going to ask you, what is the maximum volume? Does everyone understand the question? So we need to come up with an objective function. We need to come up with a constraint. So what is the objective function? What is the thing we're trying to find the maximum or minimum of? The volume, right? So the objective here is to maximize, right? Find the maximum volume. So I need an equation for volume. Volume is equal to what? Length times width times height. Now I have not labeled anything here, right? Do you know the length? Do you know the width? Do you know the height on this? Not really, right? But so let me just put down L capital, I'm using cursive, length times width times height. I don't write in cursive very often, but there's some cursive for you, all right? Volume is length times width times height. That's just from our general knowledge of what volume is, right? But I need to come up with the formula that relates it to this picture, right? So, what's that? Yes, that will be the height. But what is that amount that you want to call it something? You want to call that H? That's fine. That's fine with me. If we call this H, these are little squares I'm cutting out, right? H like that. I was going to call them X, but we'll call them H. It's not any different to use that H. When we cut that, right? When we cut that, then fold things up. Can you tell me what this length is now, or this right here? Can you tell me what that is? 15. 15 was the original width, right? From here to here was 15. But when you fold it up, right, fold up everything, it's only going to go from here to here. Yes? From here to here. So it's the 15 you had before, but then you took off H from each end. So that's 15 minus 2H. Agreed? So this is 15 minus 2H. What about this side over here? How long is that side? This one right here. That's the 24 that you had, then you took 2H off each side there. Understand? Then how high is it? And that's where you were saying H, right? Because when you fold up the edges, right, when you fold up the edges, that height of this box is now however long this cut was. Make sense? So now the volume is what? Volume is length. We'll say the 24 minus 2H is the length, times the width, which was 15 minus 2H, times the height, which is just the height. Now, do I have a constraint? I do have a domain restriction, right? But as far as a constraint equation, I don't have anything. There's nothing else in the problem that they've given me, right? Like they're not telling me the surface area has to be a certain value or anything like that, right? I just have a function, and I know that the H must be, well, there's a maximum the H can be, and there's a minimum the H can be, for sure, right? H is how much I cut off. So let's get back to that. But does everyone understand that there is no constraint? So I would like to, though, point out that we do have the volume as a function of H. What was it? Wait, no. Was it 24? 24 and then 15, right? We do have a restriction on H. And I believe it's going to be a closed interval also. Because if I take this cardboard box and I cut out a square, right? I can make it a real tiny square, or I can make it a bigger square, but there's a biggest square I can have. What would that be? 7.5. Because look, the whole way, the shortest distance you have is 15, right? Inches across. So I can't say x can be 15, or h can be 15, because h has to be the measurement across all, from both directions. So I can only meet in the middle, which would mean h could come out 7.5 inches this way and 7.5 inches this way. Does that make sense? After that, it doesn't make any sense. They overlap each other. So I can give myself a restriction that h must be less than or equal to 7.5 inches, and then it has to be greater than or equal to 0. That is a closed interval, isn't it? So I'm trying to find the maximum value of a function on a closed interval, so I'm going to use the closed interval method. First thing I'm going to need is the derivative of the function. And I don't feel like doing product rule on that because there's three things being multiplied. So I'm actually going to multiply it all out first, then do the derivative. So the volume in terms of h is, let's see, multiply that. It's 24 times 15. Let's see. Okay, 360. I'm just foiling this, right? And then negative 28 or negative 48h minus 30h plus 4h squared, but then all of that times h. So clean that up. We get 360h minus 78h squared plus 4h cubed. Is that all right? Now, to do the maximum minimum on a closed interval, we take the derivative, right? We find the critical number, so we take derivative, set it to 0, figure out where it's undefined. So here comes my derivative. The derivative v prime, I'll just say v prime of h, is equal to 360 minus 78h plus 12h squared. Yes. Thank you. So I'm already mentally on a couch watching football, eating turkey. All right, so now that's always defined, right? So I don't have to worry about this being undefined, but I do need to figure out where it's 0. So how am I going to figure out where that's 0? Set that equal to 0, right? And fortunately for me, it's a quadratic. I'm glad it's not cubic, because for quadratic, I can use quadratic formula, right? Or I could try and factor it, but I made this problem up, so I don't think it's going to factor nice. So, yeah, but after that, is it going to do anything nice? I doubt it. So go ahead and let me get the answers real quick. Does it? They're all divisible by 12, but then is what left, does that factor? Hold on, I'm looking for my missing calculator real quick. I think I left it at home. Okay, so I'm just going to have my calculator solve this. Sorry, this is not my calculator, so there we go. I have 12 squared. Oh, it is nice, isn't it? Did you get x is 3 and what? 3 and 10? H is 3 and 10, sorry. H equals 3 and 10. The chances of that working out that nicely, that's completely random because I made those numbers up and I did not intend for them to work out that nice. So 3 and 10. Now what? So what's the closed interval method say? I take these numbers, plug those numbers into the original. Remember, the endpoints are not test points, right? Test points go into the derivative. So I plug the endpoints into the original function, and I plug the critical numbers into the original function, right? Original. And I'm just looking for the biggest one. But I do need to throw one of these out, don't I? I need to throw out 10, because 10 is not in my interval, 0 to 7.5. So right now what I need to do is the volume at 0, the volume at 7.5, and the volume at 3. And those go into the original volume equation. You should get 0 here. You should also get 0 here. Do y'all get that? No, oops, 7.5, you get 0. So if I plug 0 into the volume function, of course that h back there zeroes everything out. If I put 7.5 in here, 2 times 7.5 is 15. 15 minus 15 is 0, so that'll zero everything out. And if I plug 3 in, well, I just got to figure out what happens when I plug in 3. So let's see. Anyone get that? I'm just going to plug it in right here to this one. So 360 times 3 minus 78 times 9 plus 4 times 27. 486. 486 inches cubed, cubic inches, because it's a measurement of volume. And since that's the biggest value, right, it's my maximum. I'm guaranteed. So let's answer the questions now. The questions were, how should I cut it to get the maximum volume? So I'm going to cut it each corner out, right? And that corner cut should be measure out how much? 3 inches. So to answer the question, cut 3 inches, 3-inch squares out of each corner. This gives a maximum volume of 486 cubic inches. There's no better way to do it. That's the most efficient way. If you want to get the most volume, that's the way you do it. You want to do anything other than that, cut it somewhere else, you're not going to get a box with as much volume as that one. Zero to 7.5. Okay, so if I tell you this is 15 inches long and then 24 inches long, and you have to come cut a square out of the corner, then it has to be able to be cut out of all the corners, right? So you could, of course, cut a 1-inch square out because there's enough paper here for that. You could go 2-inch square, 3-inch square, but at some point, halfway, right? Then coming in the other side halfway, you would have to meet in the middle. So 7.5 is the most you go. Of course, when you do that, you have no height to it at all. So that makes sense? I mean, not no height. You have no width to it if you did that. You see how important it was, though? Because if you had said it was between 0 and what, 15? Then 10 would have been part of your answer, and it would have been misleading and would have been incorrect. Perhaps. I don't know. We'd have to plug 10 in and see what happened. It would have been a negative number? Yeah, so 10 here. That would be positive. Negative. It'd be negative, which wouldn't make sense. So we still would have thrown that one out, but you would have just got more lucky than anything else. Okay, let's look at another one. Well, find the point on the curve y equals square root of x closest to the point 3, 0. You've probably never seen a problem like this before. So let me draw a picture of what's happening here. You have a curve. Y is the square root of x. Y is the square root of x looks like this. Right? That's what y equals the square root of x looks like. I agree my picture's not that great, but you get the idea, right? We know that if you plug 1 in here, you get 1, right? You plug in 2, you get something. 3, you get something. 4, you get what? Square root of 4 is 2. See, my picture sucks. The question here is for us to find the point on that curve that is closest to the point 3, 0. The point 3, 0, 1, 2, 3, is just 3, 0 on our x-axis. It's right here. What point is on that curve is closest to this point? Right? So it's not as easy as it may seem, because if I just go straight up, right, that distance is more than the distance from like here to here. Do y'all see that? And so the question is, well, what is that shortest distance? What point on the curve would get us closest to that point? So, you know, when would something like this apply? You know, we can model the paths of meteors and comets and things like that, the planets going around the sun, things moving through our solar system. We have mathematical equations that give us the paths. And so we could just say, basically, this is the path, and then this is the Earth, and we want to know the closest it's ever going to be, something like that. Or satellite, you know, a man-made satellite moving through space. I mean, all these different things that we could try and figure out when this distance would be the least, right? So with calculus, we're going to be able to do this. So let's first start by trying to come up with the objective function. What's the objective function? Bless you. What is it that we're trying to find? The biggest or smallest of something? Closest. So I want the closest, smallest. I want the smallest what? Want smallest distance. Good. Want smallest distance. Have I told y'all that I actually enjoy your class? Have I told y'all that? You don't understand how good it is to be able to talk and ask a question to a class and have a response. I mean, I ask questions in this class, people answer. Not everybody, but people answer. I don't know what it is, but in some classes, I swear, I cannot get people to talk no matter what I do. I even tell them, I need you to talk. I need you to talk. Come on, let's talk. Nope, nothing. They just, well, the 9 a.m. one, and then, I mean, but there's, yeah, I know. And then there's others that are like, you know, later in the day too, but I mean, there's no excuse for it. I don't know. I mean, some people just don't like to respond. That's cool. I understand. But it's like, I just need at least a few people to want to respond. All right. Okay. So we want the smallest distance between what? 3, 0 in the graph, right? But here's the way I want you, well, Yeah, well, let's just do that. You said between 3, 0 in the graph, so I'm going to go with that. Everyone okay with that? How do you find the distance between two things? Don't we have a formula for it? What's the distance formula? So we have to go back and kind of recall from like college algebra or something like that. If somebody gives you 2 points, let's say x1, y1, and they give you another point over here, they call that x2, y2, then we can connect them with a straight line, and we can define the distance between them, which I will call little d, as what? Do y'all remember what it is? That's slope. You're doing some slope thing there. Look, check this out. It can come from this right triangle. So d, by Pythagorean theorem, it should be this side squared plus this side squared is this side squared, right? So I have something like this. D squared should be equal to this side squared, which is the difference of the x coordinates, right? I mean, moving from here to here is how much your x changes. So I can say, how about x2 minus x1? And then squared. So that side right there is like x2 minus x1. This side right here would be what? y2 minus y1. So that side squared. y2 minus y1 squared. And so that's y2 minus y1. This side is x2 minus x1. And so what we normally did was we said, okay, then d is the square root of this, right? Now, do y'all remember this formula now? Now that I put it up here, you've seen that before? But, I mean, this is where it comes from, right? This idea. Okay, so now we want to know the smallest distance between 2 points, yes? One point that we have is not moving. It's 0, 3. No, 3, 0, right? 3, 0? 3, 0. The other point does change, right? It depends on x. So what I'd like to do is go back up to my picture. Let's call the point down here, let's call that our we can say x1, y1, or we call it x2, y2. I really don't care. I'm just going to call it x1, y1. Is that all right? That's one point. The other point that lives on my graph, I don't exactly know where it is, right? That's what I'm trying to figure out. So I'm going to call it, well, it has an x-coordinate, so I'll call it x, and then the y-coordinate is, I could call it y, but because it lives on that graph, it must be what? A function of x, but what is the function of x? Which is? So if this was 4, this would be what? 2. If this was 1, this would be 1. If this is x, this would be the square root of x, right? Do you agree? The x-coordinate is x, then the y-coordinate is the square root of whatever that is. You with me? Okay. Now, what's the distance between those points? And I'm calling this one, let's say, x2, y2. So let's just plug into the formula. Here's x1, y1. Oh, wait, what was x1, y1? 3, 0? x1, y1 is 3, 0. x2, y2 is x root x. Let's plug into this formula right here. And that would give us the distance between those points, wouldn't it? The distance would be equal to the square root of x2, which is x, minus x1, which is 3 squared, plus y2, which is square root of x, minus y1, which is 0 squared. Let me clean this up. The distance is the square root of x squared minus 6x plus 9. No, yeah, plus 9 plus x. So distance is square root of x squared minus 5x plus 9. So what did I do? I just FOILed this out, right? X minus 3 squared, you do a FOIL. It gives you x squared minus 6x plus 9. Then over here, root x minus nothing is root x. Root x squared is just x. So then put that x with the negative 6x, and I get this. Yeah? This is my objective function, right? I want to know when this distance will be the smallest it can ever be, right? This function represents the distance between 3, 0 and an arbitrary point on that graph. Do y'all see that connection? Just tell me when that's the biggest it can be. No, smallest, right? We want smallest. Tell me when that's the smallest it can possibly be. That's what we're looking for, right? So are we on a closed interval? Are we on an open interval? What's your restriction on x? Is there a restriction on x? Take a look at this picture. Well, 0 is the smallest it could be, right? Including 0. And then, how about how big can it be? Yeah. The x value, though. The x value. It could be 1, it could be 2, it could be 3, it could be... Do we agree that, I mean, anywhere past 4 doesn't make sense? We're going to be further away? But technically, is this an open or a closed interval? It's open, right? Because technically, you can't stop x. X can go forever, can't it? I'm going to treat it like an open interval then. That's the way I'm going to do the problem. And plus, we need to practice seeing both, closed and open. So what I'm going to say is this. Here's my objective function. I know that the interval I'm looking at is from 0 to infinity, even though it wouldn't make sense to go that far. How do we find the max or min of a function on an open interval? Take the derivative, right? Find the critical numbers, right? Then, after we find the critical numbers, pick test points, plug those test points into the derivative, and be looking for what? In this case, we'd be looking for our function to be going down and then back up. That's what we're going for. Down, then up. Understand? So let's do derivative here. It's d prime time. The derivative, d prime, will be equal to, what's the derivative of the square root of something? 1 over 2 times the square root of that something. It was x squared, was it minus 5x plus 9? Okay. Then chain rule says times the derivative, what's inside? 2x minus 5. That's it? Okay? So I'm just going to rewrite that. That's 2x minus 5 over 2 root of x squared minus 5x plus 9. And I would like to know when that's 0, right? Well, d prime is 0 only happens when the numerator is 0. And that only happens when x is equal to 5/2. Are there any other places where it's undefined? Is that derivative ever undefined? Ooh, is it? Ooh, is that ever undefined? Well, we can sit here and think about it algebraically, right? Or we can think about it from where it came from, all right? So I think if you look at a quadratic function and someone asks you, is that ever going to be negative? It's difficult just by looking just right off the bat to be able to say yes or no. But think about this. Where did it come from? This is it right here. This is what I'm concerned about. Is that ever negative? Is what's underneath here ever negative, right? That's what I'm concerned with. Well, what's that? Yeah, look at this. It comes from this, doesn't it? It comes from this right here. I don't care what you give me as x. If I square it, that's going to be positive, right? I don't care what you give me here. If I square it, it's going to be positive. Worst case scenario is that I get 0, right? 0? So is there a place that would make this thing 0? Can this whole distance ever be 0? Why not? It's the distance between what 2 points? These two, right? Geometrically, can that ever be 0? I mean, it cannot be 0. It can never be negative too, right? If our formula is correct, which I think we're happy that it is, if it represents the distance between those 2 points, it will never be negative and it will never be 0. Yes? So I can pretty much rest assured that I'm never going to have a domain issue of this thing being 0 or being a negative number underneath the root. So I'm not even concerned. Yes? So d prime being undefined or not existing is not something I'm concerned myself with. So I would go straight to a number line now. 5 halves would go here. I need to pick something to the left and to the right, remembering also that at 0, that's where my domain ended, right? It was from 0 forever. So I can't pick something over here. So what's something to the left of 5 halves? 1. Something to the right of 5 halves. 3. I'm plugging those into the derivative. Now, it's just the top I'm worried about, right? I know the square root of all this junk. I know that's going to be a positive number. I know it. It's impossible for it to come out negative because it's the distance between the 2 points. So 1 goes up here. What happens when I plug in 1? I get a negative, so that tells me my function is decreasing here. I plug in 3 up here. 6 minus 5 is positive, right? My function is increasing here. Therefore, I have a local minimum, and that's the only minimum I have. So it's got to be the minimum. It's going to happen at x is equal to 5 halves. So I have a minimum at x equals 5 halves, which of course is 2.5. Now, what is the smallest distance? That's where it happens, right? What is the smallest distance? Plug that into the actual distance formula, right? Take 2.5, plug it into the distance formula, which would be any of these. I would just plug it in right here, and you get the formula, or you get the distance. So I'll do that real quick just to actually figure out the distance. So I'm going to go 2.5 squared minus 5 times 2.5 plus 9. Then I'm going to take the square root of that answer. 1.65 something. Anyone else get that? Yes? Minimum distance is what you get when you plug 2.5 into the distance function, which is 1.658 something, approximately. The original function, the original function, d of 2.5. The original, not the d prime, the d, which is any of these. I used the last one. I got 1.658. Yeah. So, also we forgot to find the actual point. Hold on. We found the minimum distance. We found the x value of the point, right? We didn't find the y value of the point, like the point on the graph. Square root of that, right? Square root of 2.5. So look, the y coordinate is the square root of x, which in this case would be square root of 2.5, which is 1.58. So as a point, it's 2.5, 1.58. That point lives on the graph. That point lives on that curve. That point is the closest point to the point 30. In fact, it is exactly well, not exactly, approximately 1.658, whatever units it is, feet, inches, light years, whatever the unit of measurement is here, that's the distance. About 1.658 of those. Okay? So again, you see a problem. I mean, we've done what? The farmer. We've done the folding up the corners. Now we've done a problem with, finding the minimum distance between a point and a curve. I mean, none of those are really like related to each other, right? They're all different completely, geometrically, but they all come down to the same thing, a function, max, min. That's all it's about. Okay, another one. We're getting towards the point. Pardon me? Square root 2.5. What I'm doing here is I was trying to find this point on the graph, right? I figured out that the x has to be 2.5. So I tried to figure out what the y is by just taking the square root of that. All right, this will be our last, I think our last problem. Unfortunately, I wish we could spend like 3 weeks on this section. These are so useful. Okay, this is another classic problem. I remember when I saw this for the first time, I was like, what? What? Okay, so here's what we've got. I've got a sphere, three-dimensional. I've got a sphere. Let's say that this sphere that I've just drawn has a radius of 1 foot. And I'm just going to keep it nice. 1 foot makes things nice, right? For radius. What I'd like to figure out is this. I'm going to take a right circular cone, which is like a cone, right? Snow cone cup turned over. I'd like to inscribe it into this sphere. Now, what we mean by inscribe is that the top part of the cone is going to touch the edge of the sphere. I'm going to bring this cone down in here like this. It's going to touch the bottom kind of edge of the sphere like this. That makes sense? You have a cone inscribed into a sphere with a fixed radius. Following me? This bottom red part touches the sphere. It actually touches the sphere. And then the top, the peak of that cone, touches the north pole of the sphere. I would like to know the dimensions of the cone that would give you a cone with the most volume. So what is the cone with the most volume that can be inscribed into a sphere of radius 1? That's what we want. Now, let's just please first understand there are many different ways I could draw a cone inscribed into a sphere. That's one way, right? I could do it this way also. I'll go a little faster here. I can make it a very, very narrow cone like this, right? Like that. Or I could have done something like this. A very wide cone, like that. Agreed? Do y'all see the differences? Each one of these has a different volume. They're not all the same volume. I mean, like in this one that I drew, the second one I drew here, I've gained height, right? But I've given up width. Here I've gained width, but I've given up height. So there's some optimal dimension of the cone where I get the greatest volume. What is it? Understand? Okay. So I'm going to write that down, kind of find dimensions of the cone with maximum volume. What is the volume? problems are, like I said before, they reduce down to the same thing. Can you come up with a function that you can find the max and min of? I mean, can you generate it or not? So let's go with what we know here. You want the maximum, right? The maximum volume of a cone, right? Which means you need to know the formula for the volume of a cone. What is the formula for the volume of a cone? Volume is 1/3 pi r squared height. Which means in order to know the volume of a cone, you need to know both its radius and its height, don't you? The radius and the height. That's no good for us because we want our volume to be a function of a single variable, don't you want it to be? One variable only, that way you can do calculus. So I need to somehow eliminate r or eliminate h from the problem. So I need to maybe come up with some sort of constraint. Well, what's my constraint? This cone must live where? Inside the sphere, right? I mean, this is an arbitrary cone right here. My constraint is that it has to stay inside of this sphere of radius 1. That somehow puts some restrictions, doesn't it? So the constraint is the physical restrictions imposed by the sphere. Would you agree with that idea? The sphere itself imposes some physical restrictions that don't allow our cone to just be whatever the hell it wants to be. It has to do something that the sphere is going to dictate. But I need to find out what it is that that sphere is doing. So here's where I guess I have to show you this, because all problems like this where you have something inscribed of something else are all kind of done the same way. And the first time I ever saw it, you know, I was kind of like, okay, I don't know if I would have thought about that. But now I knew that and I could go on with my life. And that's what I'm going to do for you here. So what I'll do is take my, just happen to bring my samurai sword with us today. I'm going to take this sphere and I'm going to cut it right down the middle, okay? Just slice it right down the middle. I'm going to take the front edge off and just let it fall to the ground. I want you to look at that cross section right through the middle of the sphere and draw a picture of it. So if you do your cross section, you will have a circle, won't you? You're looking at that cross section? And inside of it, you will have a what? A triangle. So now these are straight lines, and that's a circle. In terms of my cone, right? In terms of my cone, my height is this distance, right? That's my height. My radius is the distance from here to here, right? To where it touches, where it would touch the edge of the circle, correct? And that's about all I know. But what else? What can you tell me? Look, all I'm looking for, right? All I want here is some constraint that's going to allow me to eliminate R or eliminate H in my equation for volume, right? So if I can come up with any equation that connects R and H together, any equation, I'm in business. Because then I can solve for H or solve for R and then plug that into the volume equation. So anything that you can come up with geometrically from this picture that would connect R and H together. What's that? Okay, Pythagorean would tell us what? R squared plus H squared is that squared, but do you know what that is? You don't? So yes, maybe back burner that idea for a second. Yes, we do have that, but I don't know what that side is, so I'm not sure if that's going to help. What do I know? Is there anything I do know? The radius of the sphere is 1. That's got to come into play here, right? So draw me a radius. Would you agree the center of the circle is somewhere about here? And the radius of the circle goes from the center of the circle to what? Any point on the circle? Is there any particular point you would like me to draw it to? The corner of the what? You want me to go down here? Why? It just seems like that might be a good thing, right? I mean, I don't know why, but it just seems like if I go to here, that might be useful. I don't know. I mean, shit, you got to try. Right? I agree. I mean, I could draw it there, but does that really help in my picture? Does that really help? No, I mean, let's start connecting things that we do know. Okay, I'm all right with that. That I'm okay with. And can I label that 1? All right. Any questions? Yes. In the problem that was given, we were told that the sphere has a radius of 1. So when I cut it in half, the distance from any point in the center to any point on the circle has to be 1. Right? That good? What would have been harder in this problem is if I would have said a sphere radius r, and I left it arbitrary, like that take-home problem I said for bonus. That arbitrary problem, this is not arbitrary. I'm giving you a fixed value of 1 here. Now what? Yes. What if it... Oh, hold on. I have an itch. What if what? That's a good question. I think what's being posed is what if the picture looked like this? What do y'all think? My thought would be that that's definitely not going to be the greatest volume. And that you're going to have to go at least past halfway, right? So it's more of just like a logical deduction. If you wanted to truly entertain the idea, you would have to take 2 cases. You would have to take the case where the height is more than 1, and then another drawing where the height is less than 1. But I think without loss of generality, we can just be like, nah, it's got to be at least 1. Is that okay? All right. Good question. Meanwhile, I'm waiting for the rest of the class to tell me what I'm doing with this. Okay, Pythagorean. What do I have Pythagorean-wise? Are you talking about, let's look at this triangle? That I agree, we can do Pythagorean on that. The problem is, I know R, right? I know 1. I don't know this side, or do I? Dun, dun, dun. Let me move this H over a little bit. Look, isn't this distance from here to here, isn't that H, right? That's H. But you know that the distance from here to here is what? 1, don't you? Because that is a radius, isn't it? That is 1. So this distance from here to here must be the whole thing, H, right? The whole distance, H, take away how much? 1, and that's this distance. Do y'all see that? So this side is H take away 1. Aren't we clever? Sure? No? Are you? Do you understand it? Okay. Yeah, but I mean, you agree with H minus 1. You're not just being agreeable. You do see it? Okay, good. Everyone else see it? You get it? Okay. All right. You understand where it came from. All right. Now I can do Pythagorean. Now I can. And what's great about it is that I will have a relationship now between R and H, won't I? It's not going to be pretty, but it's going to be a relationship. It's going to be this R squared plus H minus 1 quantity squared must be equal to 1, and 1 squared, which is 1. So here's my relationship. R squared plus h minus 1 squared must be equal to 1 squared. And so we get r squared plus, I think I'm going to leave it, h minus 1 squared. See, I'm thinking out loud. I'm not even really changing anything because I just remembered our formula, doesn't it? Our formula for volume had 1/3 pi r squared, didn't it? So I already have r squared here. Can't I just solve for r squared? Just leave r squared here and move that stuff to the other side. And I will directly be able to substitute for r squared 1 minus h minus 1 squared. Understand? So now let's go back to our volume function. Our volume was 1/3 pi r squared h, which I've now reduced to be 1/3 pi r squared for me now is 1 minus, I am going to multiply that out, sorry. I'm going to go ahead and do this. H minus 1 squared, I'm going to go ahead and multiply it out. It becomes h squared minus 2h plus 1. So it's going to be negative h squared plus, but then minus, right, 2h, and then plus 1 is going to become minus 1. Hold on. Plus 2h minus 1. Did I lose y'all? I'm sorry. This right here, h squared minus 2h plus 1, but then I changed the sign. So negative h squared plus 2h minus 1. And then the 1's cancel. And then I distribute this h through the remaining 2, and I come up with volume is 1/3 pi, and then I'll do in parentheses now. What? Negative h cubed plus 2h squared. Bam. There we go. Look at that. I've got my volume in terms of a single variable. How about that? Do you have any restrictions on h? What's the smallest h could be? 0. What's the biggest h could be? 2. Twice the radius, right? Closed interval method. All I need is a derivative, right? Take the derivative, find the critical numbers. Any questions? Because I'm about to do derivative. We're about to be done. We're about to talk about the exam. So are there any questions here? Derivative time? Okay, just look at your h here. The smallest it could be is 0. The largest would be if it goes all the way down to the bottom, which would be twice the radius. And the radius is 2, right? I'm sorry, the radius is 1. Twice the radius. Sorry, yes. How about the derivative now? The derivative of this, now the 1/3 pi is a constant. 1/3 pi is a constant, so I'm just going to leave it here. Now I'm going to do derivative of this piece in here. Negative 3h squared plus 4h, right? That's my derivative. I set that equal to 0, which means that I don't care about the 1/3 pi. I just need to set this to 0. So that means negative 3h squared plus 4h must be 0. Because if I set that equal to 0, I could just divide the 1/3 pi on both sides and it would be gone. Right? Sure? Okay. So here with this one, I'm going to just factor an h out. Plus 3 equals 0. And then set each of these equal to 0. You get h is 0, and h is 4/3. You have a question? You want to know what happened to 1/3 pi also? Yes? Okay, this right here, I set that equal to 0. And because this is multiplication right here, I can divide both sides by 1/3 pi. And they're gone. And then over here, 0 divided by anything is 0. So all it really turns out to be is this piece equals 0. That's right. The derivative of a constant times a function, it comes with it. Like, what's the derivative of 4x? It's 4. Because the 4 stays, the derivative of x is 1. Right? You don't say derivative of 4x is 0 because the derivative of 4 is 0. The derivative of a constant by itself is 0. The derivative of a constant times a function is the constant times the derivative of the function. Yes? All right, so I have my two answers. I'm going to draw a number line. Oh, no number line. Right? Closed interval method. I'm just going to plug into the original function 0, 4/3 and 2. Now, look, do I really even need to look at those two? No, because, look, if it's 0, if the height is 0, the volume's 0, right? If the height is 2, then you can't have any width to this thing, right? Do you agree? So we should get 0 volume also. I know those two are going to be 0. But 4/3 I have to plug in into my volume function, which was 1/3 pi times negative 4h cubed. I'm just going off memory now. I think I'm wrong. That's negative 3 plus 4h. Shit, forget it. Okay, negative. No, I'm looking for the original function though. Here we go. Negative h cubed plus 2h squared. Negative h cubed plus 2h squared. That's what I'm plugging into, right? So I'm plugging in 4/3 into that. 1/3 pi, let's see, minus, what's 4/3 cubed? 64/27 plus 2 times what's 4/3 squared? It's 16/9. And then whatever that number comes out to be. That's going to be my maximum volume. Is that okay or not? I don't know. What is it? 1/3 pi minus 64/27 plus, let's see, that's 32, and multiplied by 3, that's 96/27. Subtract, I get 2, I get 32/27 times 1/3 pi. I'm just doing this in my head, so I don't know. I might be off a little bit. Okay, so let's see. Pi, I'll feel better if we have the same thing, times 32 divided by 3 divided by 27. What did you get? 3. I got 1.24. 1.24. Okay, so I'm thinking this is about 1.241. This is the volume. That's the volume of this thing. What are the dimensions that give you the maximum volume, though? What are the dimensions? We said it happens where? When h is what? 4/3? So this happens, we get a maximum volume when h is 4/3. When h is 4/3, can you tell me what the radius must be? See, I want to know the dimensions of the cone. You have to go back to where you had R and H connected, and that was way back here, right here. This was it. This was our connection. So you'd have to come all the way back here. You'd have to plug in for H 3/4, square, do all that crap, and then you get what R is. What would it be? 3/4 in there, so that's going to be negative 1/4, 1/16, 15/16. So yeah, 15 divided by 16, and then square root of that. 0.9. What did you say? Oh, was it 4/3? Not 3. Oh, it's 4/3. So that's going to be 1/3, 1989. So 0.94, 2 something. So H is this, which gives us a radius of 0.942, 8 something, whatever. Those are the dimensions that give us the maximum volume. Maximum volume is 1.2411. Okay, that's it for optimization. We won't do any more. I think for homework, you need to practice some of these problems. You're going to see at least one of these on your final. One of these is going to be on your test. But the one I put on your test that's coming up on Wednesday is going to be very basic. We're talking like farmer type problem, like the one on the review, where it's a basic setup. It's not like inscribing a cone in a sphere. It's a little more involved. So for recommendation, something like homework number 7, 8. I think I may have told you I'll do these already. Number 9. 10. 11. Sorry, I'm just as I'm going. 12. That's good. 12. 15. This is page 238. Those are like easier type problems. Those aren't very challenging when it comes to optimization. Okay, let's talk test. I sent out the review for the test. It's a lot of problems. The intention was to get you to practice. My feeling was that if you could do those problems, you'd be in good shape for the test. With that said, you all know where the review was? I emailed it, right? So are there any requests? Now, if you request something that I already did when I met with that study group, I recorded that video session, and you can go back and watch it. I'm not going to do it today. So I'm only going to do problems that haven't done. I'm just looking for my sheet that has it. I'm not going to work the bonus today. It just takes too much time. I'd rather review. But I'd be happy to work the bonus some other time. Yeah, but if you have the bonus, you can turn it in. Here they are. Okay. So, requests. Number 3. Okay, so number 3 are all max-min closed interval. I will mention this also. On the review, I give you like number 1, part A through F. They're all finding derivatives of logs, hyperbolic trig functions, inverse trig functions. Number 2 is finding y prime using logarithmic differentiation. On your test, I will not tell you use logarithmic differentiation. Like, you will have to recognize the problem and use the approach. Given your experience, you can recognize these things now. So I'm not going to give you as much direction. On the review, I wanted to make sure that you kind of were not like, I have no idea what to do. Like, at least that guided you a little bit. All right? Now, when it comes to max min on closed interval, it's going to be pretty obvious. I will say find the max min on, find the max min. I won't say on a closed interval, but I will give you a closed interval right next to it. So that will tell you closed interval method. So which one of those would you like? A, B, C, D, E, or F? Was that B? B is in Bravo? Okay. 3B. So I give you a function f of x equals x cubed plus x squared, thank you, minus 8x plus 5. That's on an interval 0, 2. And we are asked to find the maximum minimum. So you automatically are thinking closed interval method, right? All you need are the critical numbers. Derivative. When's the derivative 0? When's the derivative undefined, if it even is? My derivative here is 3x squared plus 2x minus 8. I want to know when that's 0. So my audio is probably going to cut out here, so let me switch batteries real fast. Just make sure it's still picking up this audio. That ought to sound pretty cool. That'll sound pretty cool in the video. Set it to 0. It's quadratic, right? Does it factor? Let's see. So depending on if your factoring is decent, this may slow you down or speed you up. It just depends. What? Thought you said it factored. You got to try something. Does that work? 4 and 2 this way? Yep. Plus, minus, like that. So that's the guess and check method, where you're just kind of playing with numbers and getting it to work out. Which a lot of the faculty here believe that that's the best method. Only because I guess that illustrates that you really have done a whole freaking lot of problems to the point where you're doing them mentally. It becomes automatic. If you're at the AC method thing, that's fine, but it's just slow. It just takes a little more time, right? So the guess and check is a little more valuable later on, and today is later on. All right, so now we set those to 0, right? You get x is 4/3 and x is -2. And now you just got to make sure before you plug these in that they fall into your interval. And -2 does not. So I am scrapping that. Now, was the derivative ever undefined or not exist here? No, it's polynomial. We're good to go. So we only have one critical number. Do I draw a number line and pick test points? No, that's the wrong method, right? Closed interval method, I take that point, I take the 2 endpoints, I plug them into the original function, and I'm done as soon as I figure out what the biggest and smallest one answers are. So I'm going to go f, the original function, at 0. I'm going to go f at 2, f at my critical number 4/3. And so I'm going to plug that into that cubic function. 0, you get 5, right? 2, you get 1. 1, I'm getting 1. 4/3, well, that's 4/3 cubed, 64/27, plus 4/3 squared, 16/9, minus 8 times 4/3, right? 32/3, and then plus 5, whatever the hell that is. Okay? You got it, Tyler? Okay. Negative 1.51? Negative 1.52-ish, negative. All right, we got two goes on that. So this is going to be your minimum, right? And then, of course, this one right here is going to be your max. So on your test, as long as you show your work and you box it and you let me see where it is, this is fine for you to just box this because I can actually tell that you plugged in 4/3 to get this value. You plugged in 0 to get 5. So I can tell exactly where things are happening. All right? Next question. Which one do you want me to do? Mean value theorem. Did I do number 4? Which one, though? I did B, so another. Which one? Want me to do C? Okay, I did B on the video this past Friday. I mean, it's a long video. It's like 4 hours or something like that. Half the time we were just telling jokes. No, I'm just kidding. I wish it was more comical, but it wasn't. Well, what I did that on Friday, I posted the video and everything I wrote down because I recorded that one also. But it's not everything. It's every L'Hopital rule problem, and it's numbers 1 and 2 completely. All of 1 and 8 completely, right? There's a lot there, but I don't think I'm going to get through this entire review. I don't plan on going home and let me graph all. I don't think so. Okay, so let me get to this one. I want to do the mean value theorem. The mean value theorem says that, what are you allowed to bring on for the test? Everything? Open note, open book? No. You can have your formula sheets that you've had before, right? Your formula sheets. I'm trying to think. I mean, is there really anything else that... Oh. Well, we'll do what we've done before. You just have one sheet of paper that you can write down steps and procedures and notes, but no worked out problems. So the mean value theorem might be something you might want to just jot down. It says that f prime of C will be f of B minus f of A over B minus A. That's what the mean value theorem states. But it says that you have to have a continuous function on a closed interval for this to work. There's somewhere inside where the derivative is equal to the slope of the secant line. This was the picture. Graph. There's a line that connects these two. The slope of that line is the right side of this equation. The slope of that black line is the right side of the equation. And then the left side of that equation is that there's some point in here where the slope of the tangent line, the derivative, is equal to the slope of that black line. That's what mean value theorem guarantees you. So you don't want to look at it graphically. You just want to do this algebraically. You want to first figure out what's f of B minus f of A over B minus A. So we'll figure out that right side. What's f of B minus f of A over B minus A? For us, it's B is 2, A is negative 1. So what's f of B? Plug in 2, you get... Plug in 2 first, you get 8, take away 4, so you get 4. Minus, plug in negative 1. What's negative 1 cubed? Negative 1, and then minus what's negative 1 squared? Positive 1, so you get negative 1, take away 1, which is negative 2. So you are going 4, take away negative 2. over, what's b minus a? 2 minus -1, so that's going to be 3. So your top is 6, your bottom is 3, so this is 2. Okay? The right side of this is 2. Now, the left side of this is your derivative. You want to take the derivative of your function and plug c into it. So what's the derivative of my function? 3x squared minus 2x, but I'm going to write 3 instead of x squared, c squared minus 2c. Everyone see that? That's 3x squared minus 2x, replacing the x's with c's. I want to know when this equation is true. Tell me what values of c make that true. So I'm going to move everything to one side. Why? Because it's quadratic, right? Quadratic equations, we like to move everything to one side. And then we try and factor. If it does, it may not. I'm hoping for the best. 3c, c. What do we have here? 1 and 2, is this going to work? I don't think so. 2 and 1, that's not going to work. It's no go. No go this way. So quadratic formula. C must be equal to, you remember the quadratic formula, right? Negative b plus or minus square root, all that. So I'm just going to go negative b plus or minus square root b squared minus 4ac, b squared minus 4 times a times c, all over 2 times a, which is 2 plus or minus square root. We got under 12 and 2, 24. 24 and 4 is like root 28, all over 6. And we can just figure out what those are. Because we have to make sure that these numbers live inside of our interval, -1 to 2. We need at least 1 to live in there. So I'll get on my calculator, I'll figure out what these are. 2 plus root 28, then divide that by 6. You could simplify it, yeah. But I'd still probably need to figure out what a root is at some point, because to get it as a decimal. I'm getting 1.21 when I do plus. Does 1.21 live in here? Yes? Okay. Then if I do 2 minus root 28, then divide that by 6, I get negative 0.54, which also lives in here. So it turns out that both of these answers work. So your solution would be both of those. What else? What? No, this would be acceptable as long as you did verify they both live in the interval. Like if one of those didn't and you wrote down both, you would lose a little bit off of that. Do you have a request? Okay, anybody have a request for 5? I don't know. I haven't done them, so. Well, you look at them and tell me which one. C or E probably is. C. Would y'all want C or E? C? All right, C. 5C. So what I need to do is find where the function's increasing, decreasing, find local max and local min. So notice you're given a function and you are not given a closed interval. Now, look, I will say the difference between 5C and 5E is that the derivative of this is going to be pretty clean because it's power rule. For 5E, it's going to be quotient rule, right? So it's just different derivatives there. Okay, derivative of this will be 4/3 x to the 1/3 minus 4/3 x to the negative 2/3. That's just power rule, right? Power comes out, subtract 1. Power comes out, subtract 1. I would like to know when this thing is 0, when it's undefined, right? Let me rewrite it first, so it's a little easier for me to look at. Just kind of rewrite these fractions. So all I did here was just the 4 and the x to the 1/3 are on top, the 3 is on the bottom. Here the 4 is the only thing on top, the 3, and then the x to the negative 2/3 drop down, so it's like this. I'm doing this so that I can get a common denominator. Put these together. So what would my common denominator be? 3x to the 2/3. So I have to introduce an x to the 2/3 here and here. And by doing that, holy moly, look at that. It's 4 what? X minus 4 over 3x to the 2/3, right? That's my derivative. Set it to 0. I'll do it over here on the side. When is that derivative 0? Only when the top is. So at x is 1. When is the derivative undefined? It is undefined somewhere, isn't it? At 0. Is 0 in the domain of the original function? Yes. If I plug 0 in, this is a well-defined function. So we have a place not only where the derivative is 0, but where it's undefined. And the graph is continuous. I mean, I should be able to draw this without picking up my pencil. Okay, what do I do once I figure out the critical numbers? If all I want to know is where it's going up, down, local max, local min, number line. Why is it what? Because here's my derivative, right? If I try and plug 0 in right here, I get division by 0. Where in the original function, if I plug 0 in, it's fine. It's okay. You all right with that? Okay. So here's my number line. It was 0 and 1, right? Plugging test points into the derivative, right? You will never plug test points into the original function. Not test points. Test points always go into derivatives, either the first or second derivative, depending on if you're looking at concavity or increasing, decreasing. All right, so I plug those into the derivative. Here we go. Let's go -1 in here. Now I'm looking at this derivative right here. Can you tell me anything about the denominator? Like all the time, what's this value? What does this mean right here? Doesn't that mean the cube root of x squared, it'll always be positive? Yes. So I can tell you right now, my denominator is always positive. So all I really care about is my numerator. So negative in here, negative 4 is -8. So that means my original function is going down over here. Then at 1/2. 4 times 1/2 is 2. Take away 4, we get negative again. Then at 2, you get positive. So where is this function going up? F is going up on what interval? 1 to infinity. Where is the function going down? -infinity to 1. Yes, I do not have to worry about the 0. Why? The function is defined at 0, so I don't have to take it out and split it up and make sure I jump over that point because it's part of my function. The derivative wasn't, that's okay, but the original function was. Yeah, the original function is what matters when you're talking about the domain or the interval where a function is behaving a certain way. All right, then that's where it's going up and down. How about local max? Local max? None, right? You have none. Local minimum? It happens at 1, right? 1, and then what's the value of the function there? Because I always ask you to give me the minimum max as a point. So plug 1 into the original function. What do you get? 1 to any power is 1, right? 1 to any power, it's 1. So 1 minus 4, negative 3. That's what I would want there. Okay, you also said for number 6. So which one from 6? How about one that has a quotient in it, since we didn't do a quotient on the last one? B? 6B. Now this is a long problem. Use calculus techniques to sketch. That means you had to do that old Bobby method thing I was telling you all about, the table, the smiles, the frowns, all that stuff. All right, so here's f of x is x plus 1 squared over 1 plus x squared. I'm going to start with derivatives because we only have 10 minutes. The first derivative of this is, how would you like to take that derivative? You want to do quotient? Power? How do you mean power? I'm not sure what you mean by that. Oh, you want to bring that up? I've never done that in class, so I'm not going to do it this time. Yeah, but if I was doing quotient, I would clean the top up. Like I would actually make it that instead. And I just turned the 1 plus x squared into that. All I did was just FOIL that out, right? Expanded this and got this, and now just do quotient rule here. What's the derivative of the top there? 2x plus 2 times the bottom, x squared plus 1, minus the derivative of the bottom times the top, all over the bottom squared. And at this point, I've got some algebra to do. So I've got to distribute or expand this out here, and then over here do that. Start collecting all my like terms together. So 2x cubed plus 2x plus 2x squared plus 2. That's the top left. And then the other part is minus 2x cubed minus 4x squared minus 2x. All of this over x squared plus 1 quantity squared. Do I get anything to go away? I'm hoping for the best here. Let me see. These are gone. 2x here is gone. That's it. That's all. So how about I just put 2 minus 2x squared on top, and on the bottom, x squared plus 1 squared. I'll get the second derivative in a second. Do you have another question? No? Yeah. So now what I would do, I might go and get the second derivative now, but because of time, I just want to make sure that you understand what you do with this. You're going to set it equal to 0, right? That only happens when the top is 0. And that only happens when x is plus or minus 1. So you just solve that little quadratic right there. And then when is it undefined? Or when does it not exist? Not happening. Because your denominator can never be 0. X squared plus 1 can never be 0. So you don't have to worry about that. So I now draw a number line. I plug in -1 and +1. I mean, sorry, not plug in. I'd break up my number line here. I would plug in test points and figure out what's going on. So at 0, it's positive. At -2, it's negative. And at +2, it is also negative. So it does that. So I'm going to have a local min and a local max. With me? Next thing I would do is the second derivative. Let me just work that second derivative out. So there's f prime. I'm also going to take a chance to rewrite f prime because I don't want to use the quotient rule yet. I want to multiply out the bottom first. It's x to the 4th plus 2x squared plus 1. So if you FOIL this out on the bottom, you get that. And that's going to be a little easier for me to take a derivative of. So my second derivative, quotient rule again. Derivative of the top times the bottom minus the derivative of the bottom times the top. All over the bottom squared. Now that one I did go back to the original. Look, this is the bottom. If I square this, it's the same as squaring this. So when I square this, it just becomes the 4th power. Then I have to clean all that up, and I don't feel like doing it. All right? But you would figure out what that numerator is, and then you would set that equal to 0. You'd figure out when it's undefined, that would never happen. Is this enough for you to go with it? Do you want to know what the solutions are? I mean, I don't know. Because this was the original denominator, right? Which turns into this. I could have just done this squared. Like this in parentheses, squared. But since this is this, what I'm saying is what would happen if you square a square already? It becomes the 4th. I can do as much as I possibly can. All right. So I distribute this through. We get -4x to the 5th minus 8x cubed minus 4x. Okay, then I go here. It's going to be 8x cubed, but then subtract 8x cubed. Here to here, -8 plus 8x to the 5th. 8 minus 8x, and then finally plus 8x to the 3rd. I moved through that quickly. That's why I'm a little concerned that I'm going too fast. X squared plus 1 to the 4th. If all my algebra is correct, I hope something's going to cancel. Is that all? That's it? Yeah, I think I took care of that already. 8x to the 3rd, subtract it, minus 8x to the 5th, add it. 8x. Man, that looks like it's right. Let me see. How many x to the 5ths do I have? -4 and then 8. So got 4x to the 5ths. X cubes. -8x cubed. And then minus 12x all over x squared plus 1 to the 4th. All right, now I have to set the numerator equal to 0, right? Yes? So if I set the numerator equal to 0, I'm going to factor out a 4x first, setting that to 0. 4x is going to come out. I'm going to be left with x to the 4th minus 2x squared, what is that? Minus 3. And that, my friends, is a quadratic form polynomial. It'll factor x squared, I hope, minus 3x squared plus 1. So this looks like a quadratic, except that it's x to the fourth x squared instead of x squared x to the first. But it still factors like this. X squared is x to the fourth. X squared times 1 is x squared. Negative 3 times x squared is negative 3x squared. You put those x squareds together, you get this, and then negative 1. Yeah? So you set that to 0. This happens to not have a solution here. X plus 1 cannot be 0. But then you set these two equal to 0, and you should get x is 0, and then you should also get plus or minus the square root of 3. So you set the 4x equal to 0, that's x is 0. X squared minus 3 equal to 0, move the 3 over, take the square root both sides, you get plus or minus root 3. Now you do a number line. Because it can't ever be 0. Right? Well, if I set that equal to 0, then I'd move the 1 over, it'd become x squared is negative 1, that's not happening. So I do this. I plug test points into the derivative. And I could actually plug those test points into this right here. Oh, no, whoa. This right there. Because that's the numerator. I know my denominator of my second derivative is always positive. So it's just a matter of what's happening here. I already know x squared plus 1 is always positive, so I don't even care about that. It's just what happens with these two. So what's something to the left of negative root 3? Negative 2? What happens if I plug negative 2 in here? Get negative 8. Then negative 2 squared is 4. 4 minus 3 is 1. So I've got a negative times a positive, which is negative. So it goes down. Concave down. Negative 1 gets plugged in. Plug in negative 1. You get negative on the outside. But then here, negative 1 squared is 1. Take away 3. So negative negative becomes positive. Plug in positive 1, and you get a negative. And then plug in 2, and you get a positive. And it won't always switch, okay? It won't always be like negative, positive, so you just have to find one and the rest are alternating. Yes, then you would come in here. What were the answers for the first one? What were our critical numbers for first derivative? Negative 1 and 1. And so I'd create that table, right? This would be f prime, f double prime. This would be f. Okay, so I have that. Then from the second derivative, I had 0. Root 3 is to the right of 1. And y'all can go if you want. I'm just trying to finish this off. So that would be our table like that. The first derivative told us we were going, what? Down till we got to negative 1, up till we got to 1, down forever the rest of the way. So down, up, down. So it goes down, then I get to negative 1, up, get to 1, goes down. The concave thing said I was concave down, then up until I got to 0, then down till I got to root 3, then up. No? Is that right? That was right? Yeah. So we would be going down the right side of a frown, the left side of a smile, the right side of a smile, left side of a frown, right side of a frown, left side of a smile. Below this, you draw your graph. You plug in these points. You plug these points into your function, right? Your original function. You plug these in, and those give you points. And which one is this? It's going to be something like this. I mean, you have to, I don't know where the x-intercepts are, but you know, it's going to go like this, and then like that, and then like that, and then like this. If the problem's a lot easier than this, I don't know. Hold on, I'm getting a call. I got to take this.